Hello folks. In this video we're going to continue with our discussion of electricity by moving into a discussion of electric circuits. So we'll provide some basic definitions for electric potential, which corresponds to what you know as voltage. Then we'll define what we mean by electric current, and basically how current flows through an electrical circuit. At the end, we'll have a brief discussion of batteries. So here we go. All right, so let's start with just a basic electric circuit, which is shown here, where we've got a battery, a copper top, if you will. And in this case, the battery's hooked up to a light bulb. Now, this is what's going to correspond to a DC circuit, which we'll talk a little bit about in a few minutes, because batteries provide what's called direct current. And when we talk about current flow, the flow of electricity through a circuit, we're talking about charge. The battery has a charge differential, and that charge differential on one side, on the one end of this battery, the terminal end, and all batteries have two terminals. One terminal is going to be positive in charge, and the other terminal is going to be negative in charge. So what we're going to note is that charge is going to flow through a circuit from a positive charge is going to flow from positive to negative. A negative charge is going to flow from negative to positive. So in the general definition of circuits, as we see here in this particular diagram, what we call conventional current. All right, and this is when we talk about current in textbooks and how current is defined. The current is defined as the direction in which positive charge flows. So we're going to note in this particular diagram that the positive charge is going to flow in the opposite direction. Positive charge is going to flow from positive terminal through the light bulb to a negative terminal. Okay, and that's the conventional definition of current. If we talk about electrons, an electron current flow, then it's going to be the opposite direction, of course. We're going to see electron current flow from the negative charge, negative terminal, to the positive terminal here in this particular diagram. So that's the basic definition. We don't need to be terribly concerned about the difference between the two in our discussions, but if you were to look in other textbooks or online, you might find a little bit of confusion there in that definition of the direction. Again, the basic idea is that positive flows toward the negative terminal, negative flows to the positive terminal. So in this case, again, we've got a battery in this situation generating the power associated with the circuit. The other thing to be aware of is that in order for current to flow, you must have what's called a closed circuit. And essentially you see that here because we've got a loop that goes through what we're powering, in this case a light bulb, but whatever it might be that we're powering, through that to the other terminal. So it's what's called a closed circuit. If you were to have a switch in the circuit, for example, we could put a switch here someplace in our circuit, and sometimes we just represent that like this. This would correspond to a switch being open, and if I have a switch open, that means it's off. If the circuit is open at all right, if there's not complete circuit, then no electricity will flow, and that means that when you turn on a switch, what you're doing is you're actually closing the circuit, and that allows electricity to flow, so that would turn on the light bulb. So that's what we mean by a closed circuit. So basically we have a simple circuit, flow of charge through a closed circuit with a power source that in this case is a battery that flows into the circuit, that turns on the light bulb, and boom, there you got it. Okay, so let's talk about some basic terminology and units and how we work with that. The first thing is the volt. You've certainly heard the term voltage, volts before when you talk about batteries, for example. You might have a car battery, and a car battery would be, you know, a 12-volt battery that's in your car. Okay, a simple AA battery is 1.5 volts. That would be a AA battery. So, and then of course your household current, which is actually AC, and we'll talk about that in a few minutes. That's 120 volts. Now, in previous videos, we've certainly used the terminology of voltage. For example, we talked about the Tesla coil in a previous video at about 50,000 volts, and that lightning and thunderstorms, you're talking about 100 million volts maybe and such like that. So that you've certainly heard the term voltage used before, but we're going to limit our discussions here to some common items and the voltages associated with those common items. And so what does that mean, this voltage, this potential difference? Well, the volt is defined as the amount of work necessary to carry a charge, to move a charge, okay? So basically, it's work divided by charge, or in our units system here, the SI unit system, a volt is defined as a joule being the unit of energy, per coulomb. 1 volt is 1 joule per coulomb. And so that potential difference that we have is a situation where we've got a charge differential between the two terminals of, say, a battery, and that charge differential leads to a potential difference, which leads to a particular voltage associated with the power. Excuse me, not the power, but the battery itself. So that's what we mean by a volt. All right, and then current. So what is current? So voltage represents this potential difference between the terminals of the battery, which powers the circuit. Then when we talk about electric current, we're talking about the rate of current flow. And so the rate of current flow, how are you defining that? We're defining that as a charge per unit time, okay? And that would be represented by this little equation here, charge per unit time. And the standard unit for current is the ampere. All right, commonly referred to as an amp, and represented by simply the letter A in that. And 1 amp is defined as 1 coulomb, coulomb being our standard unit of charge, per second. So that's what we mean by current flow through a circuit. Okay, so some basic equations that we're going to be associated with this, and I see there's a typo here. So again, the voltage or the potential difference is volts is equal to the amount of work per unit charge, and again, joules per second. Current is defined as the flow of charge per unit time, the rate of flow of charge. And then we've got this thing called resistance. Okay, the resistance is just what it sounds like. It's the resistance to current flow through a circuit. And that resistance depends on the various items in the circuit. It depends on the wires, for example, the metal conductors that are used in the circuit itself. And so it depends on those conductors. It depends on the properties of those conductors, things like the diameter of the conductors, the metal that's used for those conductors. They all have different properties. So the resistance depends on that. It also depends to some degree on temperature. We're not going to go into all of that here at this point. So that's resistance. And the resistance is equal to the voltage divided by the current. And in fact, more typically, you would see this equation written as the voltage equal to current times resistance. And this is called Ohm's law. Okay, that's the voltage is equal to the current times the resistance. What are the units of resistance? Well, the units of resistance, of course, are based on the fact that the volts is a joule per coulomb, and the current is a coulomb per second. The resistance in the circuit, when used in this equation, has a unit which is called the ohm. Which is given the symbol omega. This is the Greek character. It's a capital omega. It's a Greek character omega. That represents resistance units. Okay? And again, Ohm's law is simply volts is equal to current times resistance. Okay? All right. So now we can talk about power in a circuit. And remember, power is defined as energy, the rate of energy usage, so it's energy per time, per unit time. And so the power in a circuit, the power generated by a circuit, is equal to the current times the voltage. All right? And again, if you work out the units here, you can see how that would work out, because current is coulombs per second, and volts is joules per second. So, I'm sorry, not joules per second, joules per coulomb. All right, and so coulombs will cancel, and we're left with joules per second, which of course corresponds to a watt, which is our unit, our standard SI unit of power. All right, so that's what we have there for power. Now I'm going to run through several calculations, sample calculations based on end of the chapter problems that you will see in separate videos. So if you want to see how these equations may be used in different kinds of calculations, you want to check into the sample calculations in the other videos in this particular module. All right, and so again, here is just a summary of the standard units that we use in our calculations associated with electrical circuits. We've got the volt, joules per coulomb, the ampere, which is coulombs per second, resistance in ohms, and power in watts. These are the standard units. Of course, we know there are other units, like one of the calculations that we're going to be working on involves horsepower, which is a unit of power, but it's not a standard unit of power. But a lot of times you will see things like motors, for example, rated power-wise in terms of horsepower. So we'll need to be able to convert between those two. And of course, our old friend Wolfram Alpha will help us do that. Let's move on to our discussion of AC versus DC. We've talked about DC, or direct current, when using batteries. And direct current just simply means that the current is going in one direction. Alternating current, however, is what you have in your household. That's the current that's coming out of the outlets in your house that powers the various devices in your house. So what is alternating current? In alternating current, as opposed to direct current, where the current is always, in the case of direct current, the current's always going in one direction. Alternating current, however, switches back and forth. So, and that's kind of represented by this little diagram here, which shows kind of a sinusoidal wave here, where basically what we have is a situation where on this side of the wave it's moving forward, and on this side of the wave, it's moving backwards. So the current is going forwards and backwards at a certain frequency. It reaches a peak, all right, so the current goes forward, reaches a peak, then comes down, goes negative in the other direction, and then comes back up and repeats the cycle. So it's going forwards, then backwards. And the rate at which that happens, and you may have heard this when dealing with household circuits, is 60 hertz. It's a frequency, which means 60 cycles per second. So we have 60 cycles per second going forwards and backwards and forwards and backwards and forwards and backwards in the alternating current in your house. So that's how that runs. Now, I'm going to leave it to you to do a little bit more research on that in a discussion forum that's coming up. All right, and finally, let's talk about batteries. Batteries, as I said, are in direct current circuits, and they're used to power the electric circuit. Batteries clearly are really, really important these days. There's a lot of very important research going on in battery technology, trying to improve batteries, because we use it in everything, in our phones, in our tablets, in our computers, electric cars, all these things. In fact, normal cars use batteries as well, but it's really important for electric cars because they're what will power these electric cars. So the research in battery technology is really, really quite important. And as I said, there's a lot of it going on right now. I'm going to leave it to you to look into that a little bit, but just some basics about batteries. And we'll probably talk a little bit more about this when we get to a discussion of chemical reactions, because batteries are in fact electrochemical reactions that are going on inside. And these electrochemical reactions, there's a process called oxidation, where the substance present in the battery is losing electrons, and that would be at the negative terminal of the battery. So that end, in this particular case, in this battery, that end is the negative terminal. The other end is the positive terminal. And so at the negative terminal, we have this oxidation process going on, losing electrons, and that loss of electrons then powers the circuit. So we get in our circuit, whatever we might be powering here, we're going to get the electrons current moving in that direction from the negative terminal to the positive terminal, as we saw earlier in one of our diagrams, the negative to the positive. So this is the motion of electrons. We represent electrons with the E with the negative sign on it as electrons. On the positive terminal, we have an electrochemical reaction where the substance is gaining electrons. That's called reduction, and that's going on at the positive terminal. So we have electrons flowing from oxidation, the negative terminal, to the positive terminal, where those electrons flowing in the positive terminal are used to reduce the substance. The substance within the positive terminal is then picking up those electrons and being reduced. So that's what we call an electrochemical reaction. And again, we haven't talked about chemistry yet, but we will, and we'll talk about these kinds of reactions in more detail. They're frequently called redox reactions for reduction oxidation. They're incredibly important reactions throughout, just not in batteries, but throughout chemistry. Reduction oxidation reactions are really, really quite important and significant. So we'll be talking about that later. So stay tuned. If you have any questions, let me know.